Hello, my name is Nicole, and I'm really excited today to be presenting on my research, Discriminating Adversarial Examples in Satellite Imagery. I worked under the mentorship of Mr. Blanton and Dr. Jacobs within the University of Kentucky's Department of Computer Science. Today, as a brief overview, I will first be going through the introduction and objectives, followed by the methodology, results, and discussion, followed by acknowledgements and references, before finally opening up my school email to any questions that you might have. First, I would like to go through the motivation and angle of attack for my project. My project was motivated by the presence of adversarial examples, or data that has been slightly changed to corrupt the model's understanding. To make that a little bit more concrete, I will explain the definition of fast gradient method. Fast gradient method is a strategy to create these adversarial examples. It alters images to maximize the loss. The loss is the quantification of the model's misunderstanding of the data, and because the loss is mathematically defined, it can be quite visually unintuitive the ways in which the images actually become changed. As such, it's important to have some kind of scalable and automatic method to detect these adversarial examples, because a human cannot be expected to do this when we are talking about the frequently thousands and thousands of examples that could go into a model's training. That's where my project comes in. It seeks to ask the question of whether special losses would improve adversarial detector accuracy. Of course, my hypothesis was that the contrastive style loss, my proposed loss, would increase the accuracy because I designed that loss to resemble the human process. That, of course, leads to my engineering goal, which was to design a machine learning model with these special losses that would perform at a higher accuracy than a baseline model without the special losses. That makes my variables pretty simple. The independent variable is the discriminator type, and my dependent variable is the classification accuracy. Now that I've overviewed the motivation, I will be moving into my angle of attack. To do this, I will divide my loss into two sections, the contrastive and the style sections. The contrastive section was taken from contrastive learning, which is a way in which the model tries to learn better summaries or features of the images. Specifically, contrastive learning states that features corresponding to images that are from the same class, the same category, should be similar in their representations. Features from images from different classes should be distant in their representations. And intuitively, this makes sense, because if the representations are already somewhat separated by their class identity, then it should be easier for the model to go in and classify these representations. Siamese networks are what makes this kind of learning possible, because these kinds of networks take in two input rather than one. As such, it makes the comparisons of contrastive learning possible. The second portion of my loss was the style portion, which was taken from neural style transfer. And while I don't actually perform any neural style transfer itself, I do use the two losses that I proposed, which are content, which captures the image's identity, and style, which captures the image's general visual appearance. The content loss can be thought of as analogous to the traditional contrastive loss because they both perform a direct numerical comparison. However, the style loss is a little different. It captures the delocalized image similarity. So my project can be thought of as a kind of analog to neural style transfer, very loosely speaking, because the neural style transfer generally focuses on comparing content and style, whereas my project also compares and contrasts the content and style of various images. The reason why I focused in on contrastive style was because if you presented this problem to me as a human, then I would focus in on these style differences in order to discriminate between adversarial and non-adversarial examples. As you can see in the left column, the adversarial images have a strange kind of rainbow perturbation to them that forms its own kind of style, and I hoped to teach the model to hone in, like a human, onto these style differences. Now that I've overviewed the motivation and angle of attack for my project, I'll be going into the methodology. My methodology can be divided into two portions. First, the generation of adversarial examples, and second, the classification of adversarial examples. In order to generate the adversarial examples, I took the Eurosat dataset, which is a dataset of satellite imagery, and I classified that dataset. That gives me the numerical responses necessary to craft the adversarial examples. At that point, I could take the adversarial examples as part of the input into my two detectors, the baseline and the contrastive style discriminators. At that point, I could compare the performances of the two detectors. In order to do this, I had a few optimization specifications. These generally tell you what kinds of models that I used, as well as their settings. So first, the frozen backbone was a ResNet 18, and that just tells you what kind of model I was using to crunch the data. The learning rate tells you how quickly the model was changing its weights throughout the training process, and the change of the weights changes the function that the model represents. The cross-entropy loss tells you that the model was performing classification. The atom optimizer tells you that I was changing the model weights using the atom strategy. These are the model architectures. Again, this is really what kind of model I was using to crunch the data. But the takeaway from this table is that the contrastive style and the baseline discriminator have very similar architectures, and that hopefully facilitated fair comparisons. These are the settings, if you will, of the models that I trained. So the meaning of these various names of parameters, hyperparameters, I'll explain these real fast. The batch size and the epochs is how much the model looked at the data, broadly speaking and loosely speaking. The weight decay is how much I encouraged the model to generalize to unseen data. The scheduler is how much I changed the learning rate throughout the course of training to try to encourage the model to hone in on a fine-grained solution. Now that I've gone through the methodology, I will then be moving into my results. The takeaway from the results was that the contrastive style model performed worse than the baseline discriminator. As you can see here, the contrastive style model had a lower mean accuracy than the baseline. It also had a lower softmax difference than the baseline. That metric is a little more difficult to interpret. The softmax difference is the difference between the softmax values. And the softmax value is what the model outputs to tell the user. The softmax value is basically, it tells you this model believes that a certain image belongs perhaps 0.8 to class A and 0.2 to class B. So those would be some examples of softmax values. And so if that difference of their values is large, that means intuitively that the model is making decisive judgments, which is a good thing. Breaking that metric down a little bit more, we can see that the contrastive style for the most frequent bin generally produce softmax differences that were not as large on average compared to the baseline discriminator. We can also see that bin's frequency has a higher or a more variable value, a lower value that was more variable, which means that the model was also more variable than the baseline, which tells us that the contrastive style model was less decisive as well as less reliable than the baseline. This is basically the summary of the data that I just showed, but basically the takeaway here is that the mean accuracy difference was larger, intuitively speaking, when contextualized by its standard error of the mean difference, and that it has more of a distinct mean difference when compared to the softmax difference, when the softmax difference is contextualized by the standard error of the mean difference. So what I mean by that is that the mean difference of the accuracy was larger compared to its standard error of the mean difference than the softmax difference, because the softmax difference mean difference was less than the standard error of the mean difference of the softmax differences. In terms of the distribution that I both showed, it can also be shown that the two models independently are actually quite decisive on their own because this distribution is left skewed for both. We can also see through this table that independently, again, the two models were actually both quite accurate on that own, suggesting that these models are performing at a capacity that is reasonably high, which means that these kinds of comparisons can be drawn with more confidence. Before moving into my conclusions, I will first address the possible sources of error. So one of the sources of error that's very important to address is drawing too many conclusions from the data. And specifically, I want to note that I'm going to be very tentative when analyzing the softmax differences because its mean difference was so small relative to the standard error of the mean difference. Some next steps would be to clarify whether that difference in model performance is really so small by looking at some other metrics, such as confidence metrics. And that will tell me whether I really did pick a good metric to represent the actual model performance difference. In terms of this float errors, the float error is a small discrepancy in the numbers that the computer is using. And thankfully, I checked that the float error scale is not the scale that I am using for the actual computations that I'm doing, so it's not likely that the float errors actually impacted the computations that much. In terms of my conclusions, both models performed quite well. They were both quite decisive as well as quite accurate, but the contrastive style model did not support the hypothesis because it was less decisive and less accurate than the baseline model. And this brings me to the most interesting question, as well as what I believe is the main implications of my project, which is why, as I try to answer some questions on how best to optimize these models. And my guess as to the reason why the contrastive style didn't work as well as the baseline is because maybe the contrastive features were not relevantly optimized with respect to the classification task. So a few of the potential causes, maybe the contrastive objective warped the semantic meaning too much, because just because something is mathematically, quote unquote, better in its representation doesn't mean that that feature is necessarily more meaningful to the model. And so that goes hand in hand with the second bullet point, which is that maybe the contrastive objective was just an inappropriate choice of loss. It's also possible that the style portion of the loss was too hard to learn. Style is already kind of a fuzzy concept in the sense that it's delocalized image similarity. So layering the contrastive objective on top of it, maybe that was too much for the model to handle. And this leads me to my next steps. One of the next steps that I would have taken if I were to continue this project is to first use more advanced adversarialization techniques. As you can see all the way back here, the perturbations of fast gradient method tend to be pretty obvious. So I want to make sure that my approach also would work on subtler adversarialization methods. In addition, I would like to see whether the convergentness, if you will, of my loss presented a problem to the optimization of the models. And that's because convergent losses are better for machine learning models because they tend to find one solution or either a family of solutions better than trying to find a lot of different solutions. And that has to do with the way that they're optimized. But basically in my project, I was trying to converge on a divergent representation of styles, which in and of itself is already kind of oxymoronic. And therefore, maybe I should instead converge to two different styles in the case that I'm dealing with images from different classes. Maybe that would perform better. In addition, I would like to see whether my loss was actually relevant to the classification task, basically checking whether there's a relationship between more contrastively learned examples and examples that were easier to detect or to classify. Some potential applications, sadly, these are somewhat limited because my project didn't work as I intended, but it is good that my project showed weaknesses in contrastive style learning, as well as ways in which maybe it's not good to detect adversarial examples. And so things that don't work are also very important in the machine learning community. And so those would be the potential applications, knowing what doesn't work in terms of solving this problem. I would like to acknowledge the help of my many, many mentors, but especially my main mentors, Dr. Jacobs and Mr. Blanton, for lending their time and their guidance to me. I would also like to thank Ms. Young for always encouraging me and supporting me throughout this process. I would also like to thank the MSTC program for making this opportunity possible and also supporting and encouraging me. And I would also like to thank the Kentucky Young Researchers Program for making this opportunity possible and to allow me to learn some really cool things about machine learning. In conclusion, here are my references. And if there are any questions, please email those questions to my school email, and I'll be very, very excited and happy to answer them. Otherwise, I hope that you enjoyed this presentation and that it was informative, and I thank you very much for listening to my research.